At the first look, the shipping capacity problem looks completely detached from a binary search or say even a search problem. However, we can ask a different question, we can cast the problem differently, and then the problem starts to look much more tractable. Instead of asking the minimum ship capacity for a given D, let's flip this around and ask a question. For a given ship capacity, what is the number of days that we need to complete the shipment? You notice we are inverting the question. We are not saying a given D, we are saying given ship capacity, what is the number of days we need to complete the shipment? For example, in the numerical example that we just took, to transport, let's say, these 6 items with these given weights, for a ship capacity of 8, we saw that we need 4 days. Now, the moment I start asking this question, we now have a kind of a list, even though it's not written that way, where we can say that, okay, look, as I go from smaller ship to a larger ship, perhaps the number of days that I need to to transport these items will keep decreasing. The smallest ship size where D days can be achieved will be our answer. Even though the list is not explicit, but you can already see it forming. Let's see an analogy. Let's say we have bunch of things to let's say transport. If I had a small little truck, well, I need to make perhaps 5 trips. If I had a bigger truck, maybe I can do it in 2 trips. If I had a very large truck, perhaps I can do it all in one trip. So the question here really is that what is the capacity that I need on my ship or my truck, let's say, to meet a certain number of days. So, the moment I start seeing this way, right, the moment I start seeing the problem in this way, then I start seeing a kind of sortedness in the data. Basically, the larger the capacity of the ship, the lesser the number of days. In fact, the interesting bit is that we start seeing a very, very clear demarcation for a given number of days below a certain size of the ship, the order cannot be fulfilled. So, for example, in our example, if an 8 unit ship cannot fulfill the order, definitely a 5 unit ship also cannot fulfill. However, once we go more than a critical number, the order can be fulfilled. So basically, there is a number out there which is the smallest size at which the order can be fulfilled. That is the number we are looking for. We again have the clear demarcation where we know, let's say if I were to look at the size of the ship and say, okay, there is this magic number somewhere below which I cannot fulfill the order, above which I can indeed fulfill the order. So now contrast this with the other problems that we just looked at. In the flight path problem, again the situation was similar. At any given index, I could tell if the optimal is ahead of me or is it behind me. In this case, basically, if I cannot fulfill the order at this, let's say, capacity, then I know that the size needed is more than what I am. If I can fulfill, then perhaps I can look back and maybe the minimum size needed is behind me. So the demarcation is very clear. Similarly, in the gradient problem, if the gradient is positive, I know that the peak is ahead of me. If the gradient is negative, I know that the peak is behind me. See the similarity, because this is the underlying principle here. The moment I start seeing this, well, I have several options opening up. First thing first, well, linear search, I can just start with the lowest value, keep going till I find that, look, suddenly, when I move from here, so basically in this region, I cannot fulfill the order, I find the first chip capacity where I can indeed fulfill the order, and that is my answer. But that again is going to be, let's say, a long process. Given that we have a clear demarcation, we know exactly if the optimal is ahead or behind. In fact, binary search becomes very attractive. So, for example, let's say I might, set 2 boundaries and say, okay, let's try the middle value. Maybe I find that middle value is not feasible, it cannot fulfill the order. So, okay, never mind. I know that anything below the middle cannot fulfill, so I'll not even look here. I will just go and look in the next middle. I find that it's, more than, I mean, it's able to fulfill the order. So perhaps there's some value in between that can also fulfill. So I can keep going in between, till I find this value. So that's the intuition here. Very, very interesting, very powerful. Really makes it quite yeah, clear why binary search is actually useful. Right? So we could do linear search, but more smarter would be to do binary search. But no matter whether we are doing linear search or binary search, in fact, we need here a helper function that can allow us to determine whether the order can be fulfilled or cannot be fulfilled. So the idea with this helper function is that, look, I have this list of weights, I have the shipping capacity, I have this number of days in which I must fulfill. Can I fulfill the order? Can I not fulfill the order? So we'll write a function which will tell us that, that, let's say, yes and no answer. And that helper function will then be used as part of binary search to narrow down the minimum capacity that I need. Very, very interesting, the thought process. Think about it, and happy to discuss. Our website www.ybyte.in has a lot of material with which you can learn programming algorithms in a fun way. Do look at the website and enjoy programming. Take care. Thank you so much. Bye bye.